Good morning. We are going to do some linear application problems that use the solving that we've been working on. So before we do that, we're going to do a pre-skill called unit analysis. And unit analysis is a way of converting units or simplifying units so that they are more meaningful. When you do unit analysis, the units cancel like numbers. And we've already done some prime factoring. It's basically the same thing except with units instead of factors. Okay, so first thing we need to do is set up a basic rate. So let's say you're doing some math and you have some units in feet divided by seconds. Okay, so remember that division symbol is like a little fraction. The first unit goes on top, the second unit goes on bottom. So to change this to a unit analysis fraction, feet would go on top and seconds would go on bottom. Now, most of the time you're looking for a unit rate, so it would be feet per 1 second. So feet per 1 second. And the word per in mathematics most of the time refers to the fraction bar. So that's how you set up a basic set of units from division. Okay, so let's get into simplifying. Let's say that one of your amounts is in kilometers per hour, and then you're multiplying it by something in the units of hours per minute. And you need to simplify those units. Okay, so the way you simplify it is start by removing the word per and creating unit fractions. So the first one becomes kilometers over 1 hour times the second one, which is hours over 1 minute. Just like prime factoring, you multiply the tops together. So I get kilometers times hours, multiply the bottoms together, hours times minutes. Hours divide into hours one time, and it simplifies to kilometers per minute. Pretty straightforward. Let's do another one, example 3. Let's say you have the units of centimeters and you're dividing it by centimeters per foot. So again, you're going to create a division, one on top, one on bottom. So on the top, you're going to have centimeters over 1 divided by, on the bottom, centimeters per foot. Now we've done these as well, stacked fractions. So to simplify stacked units like this, you need to multiply the bottom by its reciprocal, which is feet over centimeters. That tells you to multiply the top by the same thing, feet over centimeters. The reciprocals on the bottom all divide to 1. Feet go into feet one time, centimeters go into centimeters one time. The entire bottom simplifies to a 1, which we can then disregard. So on the top, multiplying the tops together, I have centimeters times feet over 1 times centimeters, which is centimeters. Centimeters divides into centimeters one time, and I'm left with feet as my final unit. So that's how you simplify units. It's using skills we already know, just in a different way. All right, Roman numeral 2. This is an example of a diagram problem. This is U.S. postal regulations. U.S. postal regulations. Okay. So in a diagram problem, they're going to be giving you the dimensions of objects, length, width, height, and it really does work best if you draw a picture and label what you have. So what I want you to do is draw a square. It doesn't have to be very big. Just like so. And then to make a three-dimensional box shape, you just count up I'm going to count up 2 and go to the right 1, 2, 3, 4, 5. Up 2 to the right 5. And you do that for each corner of the box. Up 2 to the right 5, 1, 2, 3, 4, 5, make a dot. Up 2 to the right 5, 1, 2, 3, 4, 5, make a dot. Up 2 to the right 5, 1, 2, 3, 4, 5. And then you connect matching corners. So do the bottom one, do the upper corner, do the left corner, connect the sides of the box. And for what we're doing, you don't actually need to have a three-dimensional drawing, so we can disregard the invisible sides. Okay, so in a U.S. postal regulation problem, they calculate the total number of inches so they know how to charge you the right amount of money. And their formula to do this is they measure the length of the box plus what we call the girth of the box. And in the length of the box, it's the long edge. So this would be your length. The girth of the box is actually the distance around the end. So bottom, side, top, side, that whole distance around is called the girth. And from that, you get to calculate the correct amount to charge for shipping a package. Okay, so in our example, you have a box that is 48 inches long and has a total sum of dimensions equal to 108 inches. So the length plus the girth is 108 inches. And they want you to find the other two dimensions. And by the other two dimensions, they mean the height and the width. Now, in this particular box, the height and the width are the same number. So we're looking for the height and the width, and both of those are same x. So we're going to label the height and the width x, and then we're going to substitute those into the formula. Length is pretty easy because the length is 48. Girth is going to be our 4x's added together. So we get 48 inches in length plus the girth, x plus x plus x plus x. That equals a total of 108 inches for the measurement of the package. Put a box around it. That's your equation. And then that's something that you can actually solve. Here's the middle. And we're not going to do the whole thing, but I'm going to start you on it. Simplify first. So x plus x plus x plus x is 4x plus 48 equals 108. And then you would just finish doing your linear solving. We end up with x equals 15 inches for the height and the width of the package. Okay, so that's our first story problem type that I wanted to show you. All right, let's go to Roman numeral 3. Roman numeral 3, graph intersection. Roman numeral 3, graph intersection. Now, we've actually already done a couple problems like this one. We did them as part of our participation in class. But basically for graph intersection problems, you need to find what's called the break-even point. And the break-even point is where usually the cost of item 1 is equal to the cost of item 2. So we're going to draw a quick little break-even graph. So draw yourself an L-shaped graph. Typically, the bottom is like time or sessions or visits. We're going to label that time, and we're going to do it in days. And then on the side of the graph, this is the quantity you're talking about. Many times it's dollars. Sometimes it's something different, but it's typically dollars. And in one of these break-even graphs, typically you have one option that starts with a $0 investment and then some kind of a rate that's pretty steep. Rate 1. And this is typically the higher rate. Now you'll also have another quantity where you pay an initial amount. So this is your initial amount of dollars, but the rate will be lower. So this is rate 2. It will be lower. So at some point, the lower rate, even though you started a higher amount of money, the lower rate will actually be a better deal. This little point right here, this is your break-even point. And before the break-even point, you're going to pay less if you don't start with the initial amount. After the break-even point, you're going to pay less with the initial amount invested. So, for example, let's say that you want to go to a gymnasium and you have a membership fee that is $75 a month. And after that membership fee, you're going to pay only $5 a visit. And then we have a non-member fee, which is actually $10 a visit. So the question is, how many times would you need to visit the gym so that buying a membership would be worth it? So on this problem, we're going to say X is the number of visits. So with the membership fee for a month, it would be $75 plus $5 a visit times X number of visits. That would be your costs. And we want to know, when is that going to be equal to $10 times X, because you're $10 per visit. This will give us our break-even point. After that point, being a member will be a better deal. So that's how you set this up, and then you solve for X. All right, so that is a break-even point or a graph intersection. You're typically comparing something that costs money. Okay, Roman numeral 4. This is for a diagram approach where you're going to draw a picture. Diagram approaches typically have measurements that are mentioned in them, and it typically has dimensions, and not just straightforward ones like the box that we drew, but measurements and dimensions that have to be used in combination with each other. All right, so here's an example, and if you want to pause the video to write this down, you can do that. It says 3 pictures that are each 2 5/8 inches wide are to be placed on a page that is 11.5 inches wide. If you leave equal space between the pictures, how much space can you put between pictures if the left margin is 3/4 inch, the right margin is 1 5/8 inches? So we're talking a lot of dimensions here. So this is definitely one you're going to want to draw out. And you want to make the drawing big enough that you can actually label it appropriately. So what I want you to do on your notes here is I want you to draw a pretty good sized rectangle so we have some room to work. And then what we're going to do is put the amounts onto the drawing. So it says 3 pictures are 2 5/8 inches wide are to be placed on a page that is 11.5 inches wide. Okay, so 11.5 inches is the width of this page. And they're going to be equally spaced. So I'm going to draw my 3 pictures, 1, 2, and 3, that are equally spaced. And it says that the 3 pictures are 2 5/8 inches wide. So this one is 2 5/8 inches, this one is 2 5/8 inches, and this one's the same. So those are the widths of each of the little pictures. And these little markings I'm putting in are just to show width. So we want to leave equal space between them, but we need the left margin. I'm going to change colors. We need the left margin to be 3/4 of an inch. So from here to here needs to be 3/4 of an inch, and the right margin needs to be 1 5/8. So this one's bigger, 1 5/8. We want to know how much space to leave between the pictures. So our x value is the number of inches between the pictures. So I'm going to label this one X and this one X. That's the distance between the pictures. Okay, so when you're setting up a problem like this, you need to look for a total. In this case, your total width is 11.5 inches. So that's what everything is going to be equal to. So your 11.5 inches is going to be equal to all these things added together. So 3/4 plus 2 5/8 for the picture plus X plus 2 5/8 for the next picture, plus X, plus 2 5/8 for the third picture, plus the right-hand margin, 1 5/8. So we're just basically adding all those dimensions up to equal 11.5 inches. Now I'm not going to do this whole problem, but you would definitely want to convert off of mixed numbers before you did anything. So 11.5, 2 times 11 is 22, plus 1 is 23. So 23 halves equals 3/4. 8 times 2 is 16, plus 5 is 21. So 21/8 plus x plus another 21/8 plus x plus a third 21/8 equals 1 5/8. So 13/8. Sorry, plus 13/8. So in order to simplify this, you're going to need your x's to have a common denominator. And I would definitely clear the fraction here as well. So I want everything to have an 8 on the bottom. So I'm going to multiply this one by 4/4 to get an 8. 3/4 by 2/2. The x by 8/8. The other x by 8/8. And now they all have 8's on the bottom. When all of the bottoms match, you can actually divide off all of the bottoms and you're left with just the tops. You have 92 equals 6 plus 21 plus 8x plus 21 again plus 8x plus 21 plus 13. Basically all the tops. And now you're all set up to solve this. Again, I'm not going to actually do the solving. You end up with x equals 5/8 inches in between the pictures. So that's a diagram attack where you're actually going to draw it out and label the dimensions and create your equation from the drawing itself. There are a couple of those on the assignment. All right, last one, last problem type, Roman numeral 5, is an algebraic approach. So an example of a algebraic approach question is this one. Again, you can stop the video and copy it down if you wish. It says at North High School, 176 buy non-spiral notebooks from the school store. This number has been increasing at a rate of about 24 per year. The number of students buying spiral notebooks is 331 and has been decreasing at a rate of about 15 per year. At these rates, when will the number of spiral notebooks sold be half the number of non-spiral books sold? So we're looking for a break-even point, actually, between the two. Okay, so what is the algebraic approach? Number one, you want to do what we call, you want to write the big picture in words of what you want to find. Okay, number two, you're going to look for totals. And, or, if you don't have totals, you also can look for what we call equal amounts, things that are equal to each other. And that usually will give you 1/2 of your equation. So you'll have something or other equals a total number, or you'll have amount 1 equals amount 2. So you want to look for those kind of relationships. The third thing you do is designate your x value, and then you build. Okay, so let's look at this question again using this approach. We're looking for when the number of spiral notebooks sold will be half the number of non-spiral books sold. So that's your big picture, is when the number of spirals, I'll just call them spirals, is equal to 1/2 of the number of non-spirals. That's my relationship. This would be an amount equaling an amount. Okay, so then what's our x value? Our x value is the number of years, because they talk about how each year things increase or decrease. So that's your x, is the number of years. And then what are the other numbers that we can group? Okay, so the non-spiral notebooks start at 176. This is your non-spirals. And it is increasing, so we're going to add, because it's going up, it's increasing by 24, per year. Okay, so then the non-spirals starts at the spirals start at 331. So these are the spirals. And this number is actually decreasing at a rate of 15 per year. So even though you start with more spirals, you're actually losing numbers, which is why eventually they will have this relationship. Okay, so let's put those into our big picture equation. So starting with the spirals, we have 331 spirals minus 15 per year, so times x number of years. We want to know, when is that equal to 1/2 of the non-spirals? They start at 176, but they are increasing, so plus 24 times each year. That is your equation. Put a box around it. Okay, so to solve this, your first step would be to simplify the right. So the left is fine, so 331 minus 15x. And then the right would be, you distribute the 1/2 to get rid of the parentheses. So that would be 88 plus 12x. And then you would just solve like normal, and you end up with x equals 9 years. So again, the big picture is important. You've got to figure out what is going to be equal or what's going to add up to a total. And that gives you the structure for your equation. All right, so that gives you several approaches to use on your homework. Good luck and have a great afternoon.